and share. So I'm going to start with I'm going to start with explaining what is sensitivity analysis all about at all. In linear programming, like in any other decision situation and optimization, the input parameters are not necessarily known with certainty, and you use them as if you do know them. So after you are optimizing and come up with an answer, you might get question of the what if type. Indeed, sensitivity analysis is also called what if analysis. So, and also post-optimality analysis, because after you finish optimizing, you now start asking questions about this optimal solution and how changes in input parameters affect the end results. For management is extremely important because they know they are working within uncertain environment. Environment is dynamic many times. What you thought would be true end up not be true. And you make your estimates of different parameters either using statistics or using your own experience or economical analysis, but there are estimates. So estimates may change. So management will ask you about the effects of those changes, and that's what sensitivity analysis is trying to answer. There will be two types of sensitivity analysis questions that we are going to discuss. And the first one will be in the objective function of the linear programming model. And the second will be in the constraints. Specifically for the objective function, we are going to let a parameter, a coefficient of a variable change. Remember the problem that we had on profit of a production plan in which you have two products, and the products are space rays and zappers. You knew the profit per each one, per dozen. Well, we may let one of these profit change and ask what will happen. In sensitivity analysis that we are doing, and this is true for the objective as well as for the constraints, one parameter is allowed to change at a time. The rest of the parameters don't, because you want to isolate this parameter and see the effect that changes there are having on the optimal solution. So we will let such a parameter, such a coefficient in the objective function change, okay? And we will ask what happens, and we will realize that not necessarily immediately something will happen. The change has to be large enough for a change to occur. All this will become clear in a minute. Look at the picture. This is the feasible region for our production problem that we did before. There are constraints. This is, for example, a production time constraint, and this is the plastic availability constraint. The green area here is the feasible region. This is where you should look for the optimal solution because all the constraints are satisfied. Outside, in here, constraints are violated, it's infeasible, and therefore the optimal solution will not be looked at there. We know that there is a single production plan that maximizes the profit here. We found it last time, and we look at it again today. So assume the objective function that is known to be 8x1 plus 5x2 is changing because management comes to you and say, we are afraid that the profit on space rays, so to remind you, x1 represents the number of dozens of space rays produced in our plan, x2, the number of zappers. 8 and 5 are the profit per dozen of each product. And they come to you and say, you know what, we believe that the profit, or we are afraid that the profit of space race is going to drop, not just drop by 50%, and it's going to be 4. So the new objective function you have to work with is 4x1 plus 5x2. You see, the 5 doesn't change, only one parameter is changing. The new objective function will look like this. So what do you see? There is a rotation of the objective function because the slope has changed. Now, why is it that the slope has changed? Because it is calculated here as 8 divided by 5 with a minus. Negative 8 over 5 is the slope of a straight line. But here it's negative 4 over 5, so it's somewhat less negative. Therefore, the rotation, and you see it becomes more horizontal because it's less negative. So now the question becomes, is the optimal solution going to change because of this rotation? So here is the optimal solution of the original, and here's the optimal solution of the new objective function. And the answer is no. Dropping of the profit per space race by 50% does not change the optimal production plan, which seems to be counterintuitive. You drop the profit so much that now it's less profitable than zappers. And still you produce the same amount of space race here and the same amount of zappers here. Well, it's counterintuitive, but it is correct. It's one of the characteristics of linear programming. Not every little change in the objective function will take the solution to a different extreme point. But now you may ask, what if the change in the profit is even larger? Maybe it is dropping more. So the rotation will be larger now, right? So I drop it to $3.75, not for no reason. You'll see why. And I say, let's see, is the optimal solution is going to change now? Well, the same extreme point here has stopped the solution at the objective function from moving up. With a little difference, there is another extreme point that does exactly this. So at this rotation here, okay, the old extreme point is optimal, but you have a new extreme point that is also optimal. So now we are starting to look at what happens if you rotate a little bit more. And incidentally, we saw, I think last time, all the points in between these two extreme points are optimal because they belong to the same objective function that is maximized. So what if we let the rotation goes a little bit more and I go from $3.75 to $2? Now, only the new extreme point is optimal, and this one ceased to be optimal. So something has happened at $3.75. There is a reason why it is happening right there, but the observation from here is, as the profit per unit of space race has dropped from $8 to $3.75, the optimal solution remains the same. This is quite revealing for management to know, because what if they have overestimated the real profit, gave you 8, but the real one is only 4, and you solve it with 8, and you come with a production plan that is optimal for $8, 8 and 5. And they ask you, hey, we found that you made a mistake. Don't worry, you did not give the wrong production plan. It's also optimal for $4 and 5. And it's also optimal for $3.75. But if it goes below $3.75, now the optimal solution changes. So you see there is a big, management should not be sensitive so much for overestimation of the profit because they have a lot of leeway. It might not be the same if it's an underestimation. We'll talk about underestimation also. So right now, in this current situation, the old solution here is not optimal anymore. The point moved to here, and you have one new optimal solution, okay? You might be wondering, why is it that at $3.75, something is happening and the old optimal solution is moving somewhere else? This is, in here, it's easy to explain. That's because you have a slope of the objective function. This is the dark line, and it is coinciding with the constraint. So they are parallel. So the two slopes are equal. Well, the slope of the objective function at this point is negative 375 over 5, which is negative 3 over 4. Oh, 3 over 4, 0.75. Then look at the constraint. Look at the constraint here. Look at the constraint of the production time written here. The slope is negative 3 over 4, same slope. Therefore, 375 is a critical value. If the profit per space rate drop below 375, you will get a change in the optimal solution that used to be here, and it will jump here. So this is one observation. Now you say, what if the profit per space rate has been underestimated, and in fact is $9, it's not 8. And management might come to you and say this. So now you say the rotation will go the other direction. If all the rotations here were counterclockwise, now you'll start to rotate clockwise. Because now the slope is negative 9 over 5 instead of 8 over 5, so it's more negative. So the line becomes more negative, the slope. So now it starts rotating in the other direction, and at a certain point, it will hit the other constraint here. So this new point here will become also optimal. And if the rotation continues, only this extreme point will be optimal, the one I'm on. And this is happening when the profit per dozen of spacers increases to $10. Look why. The slope here is negative 2 over 1. And if you look at the objective and say 10x1, 5x2, the slope is negative 10 over 5. It's negative 2 again. So now you have a new situation. Between $3.75 and $10 profit of the space race per dozen, the old optimal solution remains unchanged. This range has a name. We call it range of optimality. And that's the observation I want you to see using the graphical approach. When we go to Excel, you see that Excel is demonstrating these results exactly. A little bit different presentation, but exactly the same results. So this was a short discussion on changing one objective coefficient, and just I want you to understand. Each coefficient in the objective function has a range of optimality of its own. If you want to find the range of optimality for the value 5 that goes with the zappers, you have to keep 8 unchanged and do the same analysis that I did here, but now you do it for 5. And you'll find a range of optimality for it. When you go to Solver, you see that for each coefficient, there is range of optimality of its own. And this was the change in objective function coefficient, one at a time. Then we go to sensitivity of constraints right-hand side. easy to understand what happens in the example I'm giving you, although can be expanded to any constraint. I chose to take the plastic constraint in our good old production problem. See, this plastic constraint is here. And I decided now to let the amount of plastic increase. More plastic becomes available. Why would more plastic be available? Because the operation manager, say, would come to management, say, look, I counted the plastic, it was 1,000 pounds. Later on, we realized we missed in one corner some more delivery that arrived just this morning. We didn't include it in our inventory. We have 100 pounds of plastic more. Now you have to go and re-solve the problem. So, because you didn't include 1,100 pounds, you included only 1,000 pounds. So what will happen? This constraint is going to move to the right. And the good news is here. Not only that the constraint is moving to the right, I have more to work with. What used to be infeasible, what used to be infeasible becomes feasible now. So I can work with this. I didn't have this opportunity before. And now you look at the graph and say, this point, the dark, this black point here, used to be an extreme point, but this constraint has disappeared, is not even here anymore. You have a new extreme point that replaces it. It's here. But then the objective function that stopped here because it was the highest it could go, can go even higher now. So now the profit is 43.63. It used to be 43.60 before. So the profit has increased because I got more plastic and the previous amount of plastic was used up. Nothing was left over. So naturally, if you add more plastic to yourself, you can use it up again and you will make or increase your profit. So you look at how much the profit has increased and it's $3.40. How did you get it? By adding 1 pound of plastic. You see, it was 1,000, now it's 1,001. I added 1 intentionally because there is a definition that goes along with this. It's called the shadow price. So the shadow price will be the change in the objective function per 1 unit increase of the constraint on the right-hand side. Our constraint right-hand side was 1,000. It became 1,001, 1 unit increase. The profit has changed by $3.40 increase. So the shadow price is a positive value at $3.40. Shadow prices can be negative. Shadow prices can be 0, which means you change the constraint, nothing will happen to the profit or to the objective function in general. In this example, the shadow price is positive, and this means an increase in the value of the objective function. Now, you may say, if I add 2 pounds of plastics, then I add $6.80 because each one is adding $3.40, and you're right. But it's not indefinite. At a certain point, adding more plastic either will make more difference anymore, or the increase in profit will be lower. To understand why is it that at a certain point, the contribution will not be $3.40 anymore, I want to go on the other direction. Take away 1 pound of plastic. Take it away, and this will drop the profits by $3.40. So I'll get out of here, and okay, and I'll do it on the editing version. This is the original amount of plastic. See this one here. I drop it by 1 pound, then I'll move it to the left. You see, I destroy my own PowerPoint. That's okay. So I move it to the left, see, And the profit function will not remain here because this one is not an extreme point anymore. The extreme point is now here. So this point from here will drop to here. As you do that, the profit needs to drop. So it will drop to here. And how much do you lose? $3.40 for this pound taken out. Now, what if I take 2 pounds of plastics? So the line here will be now lower and the profit will be lower because the extreme point will keep moving along this line. And that's the key. It is moving along this line all the time. So the rate at which the profit drops is 340 all the time, which means the shadow price remains 340. But if I drop it all the way down, the plastic goes so much low that I stop here just for us to discuss it. The extreme point is moving along this line like this, each time for a different amount of plastic, and stops here because now we have a feasible region that is this triangle. And the profit will go here. See? So it went down. It went down, but for each additional amount of plastic taken out, you lost $3.40. The shadow price did not change. And here is the key. What happens if I take more plastic? Now I take more plastic and I stop here. Let's see. I took more plastic, okay? You want to continue the same process? Go ahead. I take the extreme point to here, and the profit goes here, and I lose at the rate of $3.40 with one little problem. I cannot move here. This is infeasible. So this situation can never happen. What can happen is if you drop your plastic, let me drop it even more. If you drop your plastic to this level and now the feasible region is here, the feasible region is here. So this extreme point is not moving along a line that is now infeasible. It has to stay feasible. So from here, it will move down and stop here. So a new constraint became active, and it forces the profit to drop even more than $3.40 per pound. And this is the observation I want you to see. You can drop the amount of the plastic, which is the right-hand side of the constraint, only so much for the shadow price to remain unchanged. This is true in any constraint. You can drop a right-hand side only so much if you want the shadow price to remain unchanged. And if you want the shadow price to remain unchanged, if you want to make your economical calculations and decision-making easier. You'll see, we'll go there. So there is a lower bound on the value of the right-hand side. I'm not calculating it here. That tells you how much the right-hand side, that is 1,000, dropped to say 600 for the shadow price to not change. You drop the plastic below that, it will change. And now you say, wait a minute, you can even increase plastic amount as I started the presentation with. So I go from here and go up, go up, go up. At a certain point, you have to stop if you want the shadow price to remain 340. Okay? So we have this range is called the range of feasibility because it stops, the boundary of the range is where the change becomes infeasible going out here. So the same is happening here because another constraint that you don't see here becomes active. And this is when you are forming a range called range of feasibility, in which the right-hand side of the constraint in question can move inside, up and down, and the shadow price remains the original. So this is what I wanted you to realize. You have such a range for the objective coefficients called the range of optimality. You have a range for the constraints right-hand side called the range of feasibility. And I want you to see how Excel is presenting this information. This is a crucial information for decision making. Okay. So I'm going now to unshare and reshare for another file. And I will see something that I believe you've seen it before. Yeah, maybe this one. It's a PowerPoint. Tell me, someone, Hector, you can talk. Tell me, did I go with you guys on this portfolio building model last time?
The last class, you mean this week on Tuesday?
You can talk?
That doesn't look familiar to me.
Maybe now. So I'm asking if the file that you've seen is one that we worked with last time. It's about demonstrating how to set up a linear programming problem for building a portfolio, optimal portfolio. Did we do that?
Not.
We did not?
It doesn't look familiar to me.
So Mr. Mendoza, tell me that we did not. Okay, so I'm going to do it now. It's one of the applications. Hey, I took it from the book. It's problem number 4 from the text. I'll work with you on setting up the linear programming, and then we'll follow into the Excel file. And I'm surprised that we didn't. I think we did, but maybe not all of you have been there. Okay, I see what happened. Because I placed the recording of this for those who missed it last time online, and there I discussed it, but I'll do it again for you guys here. Repetition is good since I don't see you guys. I don't. And I don't get the feeling as I do in the classroom about how well the class is doing. So I don't mind. I don't really mind if we repeat something here. Okay, so I'll go back to the PowerPoint that I wanted you to see. And I'll go back. Yeah, this is the problem I want you to see. It's one application quite popular from finance, in which you are trying to optimize building a portfolio based on rate of returns that you try to maximize their total. So a bank has a free new funds of $1 million. He wants to distribute the funds and use them in loans of different types that he's giving to customers. So the number of loans, 3, home loans, personal loans, and auto loans. Here is the rate of return, annual rate of return for each one. The bank is putting restrictions on how the portfolio can be built. Usually it's done because of diversification and protection from risk. At least 40% of the funds should be allocated to home loans. Home loans are the lowest rate of return. Why at least 40%? If you don't put it, chances are that this will not get even $1 single. The bank doesn't want that. Secondly, when the rate of return is low, so is the risk. The risk goes with return. For example, home loans probably have the highest risk. So they want to protect this, to safeguard from losses. They put a minimum allowed amount required in home loans. Personal loans cannot exceed more than 60% of auto loans. So these two are the second and first best. And this one has the chance to get all the money if you just want to maximize the return. And so between the two of them, he says, don't put more than 60% in here that you put here. And now let's set up a linear programming model that does just that. To maximize the return, you take the return, multiply by the variable. So our variables are the amount of money that you put in each loan. HL, home loan, personal loans, auto loans. So that's the dollar value in each one. You take 07 times the dollar value, you get the annual dollar value of the return, home loans, plus personal, plus auto loans. This gives you the total annual return, the dollar value that you try to maximize. Here are the constraints. You can only use your $1 million. So you add all the investments equal $1 million. Now, home loans, and I'm just following the restrictions from here, have to be at least 400,000, that is 40% of the million. And you have the personal loans that cannot exceed, you see, cannot exceed means less than or equal to 60% of the auto loans. This is a linear programming model that you will have to be able to set up as you solve your own problems in chapter 12. Now, we want to enter this into an Excel spreadsheet so that the software that optimizes such a model can read. The software is called Solver. So yeah, at home, if you can, I added a constraint of my own here last night that should replace this one, not because I want you to solve it, just to see that you know how to treat it, that's all. Okay, so we are going to linear programming, and the first one is a problem that we did last time, so I skipped that because I'm doing a different problem. This just summarizes, here is the building problem. We want to do a linear programming for Excel, and I just repeat the model here. Now, here I am showing to you an intermediate presentation of the same model that you see above, that is written in a way that will explain where is the spreadsheet model comes from. Each variable needs to have a coefficient. The coefficient in the objective function for each variable is given. In here, the constraint number one, on the left-hand side, you have only one variable. No, you have to have all the three of them. So the variable that appears with the coefficient 1. I'm talking about this here. The variable PL appears, so you add 1, and you add 1. So now the constraint is written is 1 HL plus 1 PL plus 1 AL equals to 1,000. It doesn't make any change in the constraint at all, but it will be easier to explain later on what happens here. The second constraint, though, has only HL here. So 1 HL, 0 on PL, 0 on AL. You see, I wrote all the three variables on the left-hand side of the constraint, but only enter the coefficient that I need. And the last one here has 0 and 0 here because only personal loans are written here. Okay? And it's greater than 0.6 of AL. I just copied it. Now I want you to see what happens as you go to the spreadsheet. And that's why I mentioned to you later, I'll talk about this. In the spreadsheet, and we are going to go to the spreadsheet now, you are entering in the first row the names of the variables. In the second row, you leave it empty. Here, Solver, your program, will enter the values that are optimal for the amount of home loans, optimal for personal loan, optimal for auto loans. This is what you will get as an outcome of the computer run. Underneath, you enter the objective function. Usually I write here, in this case, I will write maximum return. And you enter the coefficient, 0.7 here, 0.7, 12, 0.9 here. And then you go to the budget constraint. You see that I give names to the constraints here. I give names because then these names will appear in the output when you get when the solution is run and you get an output, you'll see these names. That makes it much easier to interpret the results. And the name is something you choose, doesn't matter what you write, something that is make it more convenient for you. So the budget will be 1 and 1 and 1. And then the second will be 1, 0, 0. You see why I wrote it here? I want you to see where the 1, 0, 0 come from, and 0, 1, 0. Personally, when there are zeros, I just leave it blank myself, because Excel understands a blank cell as 0. But if you want to write 0 and make it clear to you, go ahead and do it. Now, a word about the last constraint here. This constraint is written in a form that is called non-standard. Standard form have the variables written on the left and a constant written on the right. The first two constraints are written in standard form. This constraint is not because you have a variable written on the right-hand side. Excel or Solver does not find it hard to solve it with it. But you have to enter here the correct thing. You have 0.6 times AL. So you cannot write here 0.6 times AL. Solver or Excel must have here a cell, a value that Solver can understand. You write 0.6, you write equal to 0.6, and you multiply it by the cell where the value of the auto loan is going to be placed. And this is cell D8. So 0.6 times D8. I saw in the book, in your text likes constraints like this. And many questions, they have such constraints, so it pays to understand how to set them up. Okay, okay. And this is the spreadsheet preparation. I'm going now to go to Excel, and you will see this model exactly, and we'll run a solution, and then we'll do sensitivity analysis. Okay. Okay, and now I'm going to the Excel model. There is already a solution here which you allow me please to delete, because I don't want you to see it yet. And we are going to do everything here from A to Z. So, okay. This is the model that you've seen. This is the entries to the model. And here, if you notice, I put 0.6 times O2. You can see it here. See? Now, you have to add information to this model before Solver can start solving it. First of all, okay, just a moment. First of all, we'll have to add here cells that calculate functions. Excel does not, or Solver does not allow you to type in a function that you want to use inside Solver. You have to type this function in Excel first, and then direct Solver to this cell where the function is calculated. That's what Solver needs. So we need to calculate the total return, and you see what I wrote here. I wrote max and the word return here. So it will put here in the output, you see the word max return. To prevent any problem with the output, I'll write the return here and not here. It's not a mistake though. And now you will see that this will be referred to as maximum return. Every constraint will be the same. Now, what do? I want to calculate in this cell here the total return per year. Solver needs it because it's going to compare different solutions by looking at the return and then give you the best. So you have to somewhere calculate the return. How do you calculate the return? So you do it this way. You take sum product, which is an Excel function, and you open parentheses, and here's what it does. It takes the value here, which is the home loan amount times 0.07. Personal loan amount times 0.12, and auto loan amount times 0.9. It takes all these products and add them. If it does this, it calculates, as you understand, the total annual return. Because the total annual return is the return times the amount plus the return times the amount plus. And therefore, what this function will be kind of a shortcut for another function that you have to turn in by hand. So what do you do here? You highlight the first array in question here, and you press the key F4 to place dollar signs in it. You'll see in a second why, then comma, and now you enter the second array. These are the cells involved in calculating the total return. Close parentheses, okay? And now click somewhere outside and you get 0. So what happened here? 0.07 times 0 plus 0.12 times 0 plus 0.09 times 0. This is what some product did and gave you the result. Now you'll see why I pressed F4. If I copy this by dragging, you know how to drag down one cell, what did happen here is that the first row remained, but the second row changed to the third. Because I did not put dollar sign on those, then they did not remain, they adjusted to the third row. What remained the same is the first one here. And you want it to remain. To calculate now the total amount of money used in your portfolio, you do 1 times this, plus 1 times this, plus 1 times this. But this is the sum product that is done here. So now I can drag it twice more. And all the left-hand sides of the constraints are now calculated properly. For example, look at the fourth one. See, it takes the first one times the last one. And all the sum products are calculated. If I put here a hypothetical portfolio, okay? Okay, it gave me a total annual return of 83,000, okay? It gave me money used in this portfolio building of 900,000, not good because I have to use 1 million. So this is not a feasible solution. I just plug in numbers so that you see what some product is doing. And the rest of the constraints are also calculated in here. And now we have to find the optimal portfolio. But that's what you need to do to make a preparation for Solver. Okay. Now we can go to Solver. Here's Solver, okay. And you already have a model here, so I'll delete it. It's the correct model, but I want you to see how we do it. So I'll delete. Okay. And I'm starting with when you click on Solver, and you know how. You click Data, and then you select Solver here. And it's an add-on. You'll have to activate it just you did with a data analysis in 361A when you worked at home. Same thing you do to Solver. So first you enter the objective function. Remember, the objective function was calculated in this cell. So you enter the cell. And make sure that the max is selected, not the min. And here, select now the cells where the variables are. The variables are here, 1, 2, and 3. So you select those 3. Okay. Now start adding constraints. The first constraint is equality, which says that the left-hand side has to be equal to the right-hand side. The left-hand side, you see, Excel is waiting for you to enter the left-hand side, so it will be the sum product of constraint 1. And change the sign, the default sign, into equal to. And now you see it's waiting for you to enter the right-hand side. Okay. Now you add a second constraint. The left-hand side is greater than or equal to, greater than or equal to the right-hand side. So the right-hand side, okay? And now add the last one, the left. You see it's already less than or equal to by default. So I click here and enter this value. This is how you enter constraints and objective in Excel, in Solver. But with the 2 more steps, you have to make sure that this one is checked. If you just open a Solver and you didn't use it before in your session, it will not be selected. So you check it because you want to guarantee that Solver is not giving you negative values for X1 and X2 and so on. And here you have to enter the simplex. If it was not selected, by default, you'll have this algorithm. Pay attention. You want a linear programming, not non-linear. So you just change it to the simplex, and this will be the only algorithm you will ever use. We are done. So we solved the problem, and you get the solution. And it tells you that you will put $400,000 in home loans, you put $225 in personal loans, $375 in auto loans, and by the way, if you multiply this by 60%, you'll get exactly $225, as you see here. Okay. Now, because I want to go to sensitivity analysis, then I click on sensitivity here and click OK. What you will get is a new tab here near there for the tab that you have open. And here you'll have the sensitivity analysis. What I did here, I just copied it for convenience in here because there are more questions in the book that you have to base your answers on sensitivity analysis. So I wanted you to have it here. But basically you will have it in this tab here, and you don't have to do it. You don't have to copy. What I do next, I'll go back to the PowerPoint where we used to be, and I copied there this sensitivity because I want you to see what's included in each one. And you see that the information is about the range of optimality and range of feasibility and shadow prices. So I'll go back. I'll go back here. We finished this slide already. You finished this one. And in fact, yeah, we finished this one. And in fact, here, I just placed all what you saw on the Excel for your for you to look and remind yourself. Here are the sum products. Here is the solver model. And here you have the portion at the bottom here that you click solve. And here you get the results. But it's not the sensitivity report. Here is the sensitivity report. First, you run this solver and obtain an optimal solution. And then you do the sensitivity analysis per request. Here is the sensitivity report, and pay attention to the upper part, okay? And now it tells you what does it mean to have allowable increase, allowable decrease. Okay, to explain what is written here, 0.07, I'm focusing now on the coefficient, objective coefficient. Why? The upper part here is about the coefficients and changes in them. So it provides you the range of optimality. And the lower part here is about the right-hand sides. So it gives you the shadow prices and the range of feasibility. So I'm starting here. Okay. The number 07 here is the rate of return for home loans, right? Okay. It can increase up to 3.125%, which means up to 10.125. And the optimal solution that you see here, this is the resource allocation, optimal value that you get when you run Excel solver. So it's copied to here. When the rate of return 07 is increasing up to and including 10.125, this portfolio will remain optimal. But if you reduce the rate of return of personal loans by 4%, so instead of 12 is 8, now the optimal portfolio will not remain the same. You have to rerun it to know what is the new optimal portfolio. Why? Because the allowable decrease is 3%. If you drop it by 4, you drop it too much. Up to 3% drop of the rate of return, this solution will remain optimal. But if you go beyond the 3% drop, now you will have a change in the optimal solution. So this is representing the range of optimality for each coefficient, not in terms of how much is the maximum value that 7 will be, 10.25 or 125. It tells you what is the allowable increase and the allowable decrease. And this is a unique number here that I'm going to talk about in a second. So I took the questions that appear in this problem and answered them here. If the rate of return of home loans change to 9% from 7, would the amount allocated to each loan type change? Answer, no. But how do you go it step by step? This is the return to start with. This is the return after the change. You identify that the change is in an objective coefficient. Now you know that you have to look at the rate at the range of optimality. So what's the answer here? The allowable increase for the objective coefficient of HL, this is the allowable increase is a 0.031. The increase, the actual increase is 0.02. So it falls inside the range, and therefore the optimal solution doesn't change. You don't have to reallocate funds to the different loans. This remains optimal. So this was the first question. Second, calculate the annual total return of the portfolio if the above return indeed goes to 9. So we do know that with 9% here, the optimal solution doesn't change. And so to find the annual return, it's not hard. Just write 0.9 times 400,000 plus 0.12 times this, 0.09 times this, and you find the annual return. What I was saying here, you don't even have to do all this. You already know that the change in the annual return is occurring because you added 2% here. So the contribution to the change is 2% working on 400,000. How do I know? 400,000 is still optimal because the optimal solution is not changing. So the solution is 0.09 times this. But what is 0.09? It's 0.07 plus 0.02. So 0.07 times this, 12 times this times this is 88,750 as we got it from the previous run. We got it as we looked at the results in Excel after Solver ran it. This is the old value of the objective function. And now just add the changes. But the change is 2% times 400,000. And this is another way of coming up very fast, very easily with the total return without the need to rerun the problem. Since you know that even if you rerun it and you put 9% instead of 7, you will get this as the optimal solution. You already know that. So this was the range of optimality and how you can go about making some calculations. Okay. Now, this is the portion of sensitivity analysis for constraints right-hand side. And I want to reiterate what is the shadow price because it's a cornerstone in this analysis. Every unit increase of a constraint right-hand side changes the objective value by the value of the shadow price. So the shadow price changed its value for each 1 unit increase of the constraint on the right-hand side, and the change in the objective function, then it's called the shadow price. The lower part of the sensitivity report is giving you all the shadow prices here and the ranges of feasibility. So it tells you how to interpret it. As long as the right-hand side of a constraint, say 100 million here, is not adding or is not increasing by more than what's in the allowable increase and is not decreasing by more than the allowable decrease, the shadow price remains unchanged and therefore can be used. That's what the analysis is telling you here. And let's see an example or two. That's question D in the same problem. The total funds available, which is 1 million, is supported now by $10,000 more. Management has decided to increase the funds for these loans, $10,000. What is the effect on the total return? Okay. 1 million becomes 1,010,000. This is 10,000 increase in the right-hand side of a constraint. Therefore, right away, we are going to look at the allowable increase. Okay, now the allowable increase here is infinity. How do you interpret such allowable increase? No matter how much you increase the amount of funds available, the shadow price will forever remain 10 cents, which means $1 increase of the return of the funds available will always increase the total annual return by 10 cents. And there is no upper bound here because the upper bound is infinity. So now we can answer the question by how much the total return will increase without the need to rerun it, because I'm using the shadow price, since the shadow price is not changing. The shadow price is the contribution per 1 unit. I'm multiplied by 10,000 units, and this is the increase in the total annual return. Now, what if I take away $10,000? I make a question now. I take away $10,000 from the money available here. So you don't have 1 million available anymore. What will happen to the total return? I'm looking at the allowable decrease. The allowable decrease is 600,000. I took away only 10,000. So I can use the shadow price for that. So the shadow price is the contribution when you increase the right-hand side by 1 unit, but now you decrease it by 10,000. So the direction of the shadow price is the opposite of what it would be if you have increased the constraint. Let's do it. The question is related to another constraint, but it's exactly the question that I posed to you right now. Currently, 40% of the funds available must be allocated to home loans. That's why the constraint is home loans is greater than 400,000, at least 400,000, right? Now, the question tells you the following. Management has decided that they are willing to relax the constraint from 40% to only 39%. So the constraint is changing from 40% to 39% of $1 million. So this is a drop of, instead of 400,000 written here, you'll have 390,000 written now. So you have a drop of 10,000. Okay, what will be then the change in the total return? First of all, a drop of 10,000 is less than a drop or decrease of 400,000. So the shadow price can be used. What is the change in the objective function? Is the shadow price, which is negative, right? Times the decrease is negative 10,000. So the final result will be an increase of the total return of 3,125. Yeah. As you see, shadow prices can be positive, can be negative, and sometimes they are zero under certain conditions that you don't see here. But we'll do it next week. We will talk about such models. We'll have quite a few examples, and for each one of them, I'm planning to do sensitivity analysis, so we have more opportunities to look at that. Okay, and this is the coverage for today. I encourage you now to take all the problems in my last email that I indicated to you that are about linear programming formulation. Do now all the problems. I limited it last time only to section A and B in most of the problems, and that's only because A was the setting up the linear programming like we did here, and B was translating it into a spreadsheet and solving with solver, but not sensitivity analysis. Now, I want you to do the rest of the question on those problems and include sensitivity analysis based on this discussion. You can read in chapter 12, read all of it. Don't stop at sensitivity analysis like I asked you before. Include in your reading also the sensitivity. It's a good discussion, well read, and I think it will be a very good contributing factor for you if you read it. And practice is a key. I'm planning over the weekend to find some more problems and solutions and send them to you so that you can practice it. Next week, for those who have the classes were taken on Monday, Wednesday, we'll have the quiz on Wednesday. And those who had the classes on Tuesday, Thursday, will have the quiz on Thursday. It will be about an inventory model, EOQ plus cycle service level. And I say EOQ only because cycle service level is part of the EOQ model. Not going to ask you about quantity discounts or production lot size, but these two, yes. And that's for the quiz. I don't know exactly how we do it. I have thinking here. We have a meeting on Thursday. So we'll start the meeting on time, hopefully with this group. I don't know, something is not working. We'll start it on time. We'll have some coverage, and then I'll give you at the end the quiz. I email to all of you, and for this you'll have, I'm thinking about an hour for the quiz, because quiz is one problem, maybe 20 to 30 minutes, then I'll give another 30 minutes to send it back to me. So this is what I was thinking this morning. I haven't decided yet how to do the quiz. Okay. Well, that's all for today. I heard, I saw some correspondence in the university emails about how to grade this semester. And it turns out that we probably will grade as usual, but students will have the option to ask for a pass-fail score grade. I don't know exactly if it's final or not, if it was voted in. It seems to me that that's where the school is going, and you will get a notification if you have not yet about it. So that's what the latest news that I read yesterday. Okay, so this is for today, and thank you for being here. I will then, some corrections in the PowerPoint that I saw I need to do, and then I'll upload it. Some of the files you have seen on Tuesday, but not all the coverage. Today, you have the sensitivity also, which you didn't have last time, okay? Okay. So no sharing anymore, and was it okay, guys? I mean, was it understood? Don't chat. Tell me. Whoever wants to talk. Alex.
Yeah, it was good. I watched the recording from Tuesday too, so it was pretty similar.
Okay, then I have to end the meeting for the recording to stop. So I'll end the meeting. Okay.
Thank you, Professor.